Good afternoon, everyone. Thank you for being here. My name is Bruno, and my supervisor is Professor Jaime Cardoso. And for today, for this VCMI talk, I presented this presentation, Attribution Methods Based on the Information Bottleneck Principle. I actually didn't know how to title it, but since most of my works are attribution methods, and most of them are based on the information bottleneck, I decided to name it like this. And just to clarify, attribution method is a visual explanation method where you try to understand what parts of the image your visual model are looking at when it makes a prediction. Just to give some context because I forgot to put it here. And one way to generate such saliences, such attributions, is based on this principle that is inherited from information theory that is called the Information Bottleneck Principle, where you have two random variables, y and x, and you want to define a new variable that will be called the bottleneck, that we call here the variable z. And the idea is to maximize the mutual information between y and z, while restricting the mutual information between z or x. And what is the idea behind this? The idea is that y is the important information that is in x, and you want to squeeze this important information through this bottleneck. So you want to reduce the amount of information that you have between your input and the bottleneck, but you want to keep the information that is important. And another thing that is important in this equation is this parameter here, beta, because it controls how strict the bottleneck is. If you start to increase this value here, this value beta, you make the bottleneck more narrow or narrower. And using this principle, these guys were able to come up with this method, the information bottleneck for attribution, where they pick a convolutional neural network. It only works on CNNs. And they put this kind of bottleneck within one of the activation maps. And the idea here is to learn a parameter lambda that you remove information for the activation map, but you want to preserve the original prediction of your network. So here, just to clarify, R is an activation map. Epsilon here is just Gaussian noise. So if you pick your lambda equals to 0, no information flows through the bottleneck. But you do not want this. You do not want to just squeeze this information. You also want to keep the information that is important to make the prediction. So this lambda variable here that has the same size of the activation map will determine which regions are important or not. Now is a bit of a complicated part here, because for you to compute the mutual information, you need to compute the expected value of the Kullback-Leibler divergence of these two variables, z given r, where r is the activation and z is the output of the bottleneck. And you also need the probability distribution of z. And the problem here is that this P of z is not possible to track analytically. So what people do is they use some kind of approximation. They say that this distribution follows a Gaussian distribution. And this approximation only holds because you are working the activation maps. And in the activations map is quite a good assumption to assume that they follow Gaussian distributions. So by doing this, they now write the mutual information between the bottleneck and the activation map using this formula, which is also very hard to compute. But the guys for information theory have this problem already solved. And it is possible to compute this the mutual information in a differentiable way. So you can somehow optimize it. So the idea is to find the lambda that we only let the important information to pass through the bottleneck. And the final loss function is basically something like this. You optimize lambda and you use the cross entropy loss between the prediction when you have lambda squeezing the bottleneck and the original prediction. And you also penalize the mutual information between z and q. By doing this, you are achieving the information bottleneck in the sense that you are trying to find the information that preserves, that minimizes the cross entropy, and thus preserving the important information that you want, but you are also squeezing the mutual information making the bottleneck more strict. And the beta value here, it controls how strict the bottleneck is. And why am I saying all of this is just to point out that you have two limitations here. The first is that you need to have access to intermediate outputs of the model. You need to access to the activation maps, and it only works with CNNs. Because if you take this to the input, this Gaussian assumption does not hold anymore. And another thing that is important, it only works for classification models. We have the cross-entropy loss here. So basically, what we are going to see in the next slide, see how to solve these two problems and see the kind of methods that we propose. And by doing this, the IBA, or the Information Bottleneck Attribution, they can generate explanations like this. You have classification model. The prediction is monkeys, for instance. You can place the bottleneck on different parts of the CNN and observe how is the final silence map. And you can also change the beta value to control how strict the bottleneck is. As you increase the value of beta here, you see that the explanations, they get more concentrated in one point. Maybe you can see, yeah, you can see. As you increase beta, you see that the explanation gets more and more sparse. So the first thing that we did, it was my first work in the PhD, was to adapt this method for detection networks, object detection. And in the literature, we do not have many methods that are aimed to explain detection. The most popular is DRISE, which is a perturbation-based method, but it takes a lot of time to compute one explanation. What they basically do is generate a lot of random inputs and see how the output behaves when you do some kind of perturbation. Sorry, the format was not kept here. But the idea now is to use the IBA for detection. And what you do is quite simple. But since the networks that we try to analyze, they have a CNN backbone, we basically put the bottleneck in the activation maps of the backbone. And then we slightly modify the loss function that does not include only now the cross entropy and the mutual information, but we also put in now a new term to account for the position of the bounding boxes that are predicted by the object detector. So this is the smooth LE1 loss. And then you try to optimize the bottleneck to assess both the cross entropy, the LE1 loss, and also the mutual information. And as before, we have beta to control how strict the bottleneck is. And you have also sigma and gamma to control which aspect of the loss you want to emphasize more. The semantics using the cross entropy or the position using the LE1 loss. Using this, we can generate the silence maps for object detection, but I'll just talk a little bit about the metrics. It's really not in the format, but okay. We have both localization metrics that you try to see if the explanation that you generate is localized within the original bounding box. So basically pick the most salient pixel and test if it falls within the original bounding box. And you also have faithful metrics, where you basically remove information from the input image. Let's say that only part of an image is considered important for the method. If I pass only this part to the object detector, we will be able to reconstruct its original prediction. And both the Gaussian degradation and the deletion insertion metrics evaluate this. The Gaussian degradation, they remove all the information instantly. You erase these irrelevant parts of the image and give it to the model and see how it goes. And the deletion insertion is a pain because it starts to remove it very slowly. You pick the most salient pixel and start to remove. Then you pick the second most and remove, and so on. And while you're doing this, you observe how is the output of the network and see how it behaves. If you remove the most important pixel, and this is the one that commands your prediction, as soon as you remove it, your output you degrade for something that is new. Okay, so this is the kind of results that we are able to compute. Using detection IBA, we see here that this is the original prediction, and this is the explanation for this prediction. We see that most of the silence map is within the bounding box, which makes sense. And what is it inside also explains the semantic more or less. And on the top row here, we have the competitor, which is the rise. And you see that we got more or less similar results. But what is the catch here is when you analyze the time, we only take 1.3 seconds to compute the explanation here. And the rise, you actually take 100 seconds. Because what the rise does is generating 5,000 different masks. It masks the input image with each of these 5,000 masks and see which one results in something closer to the original prediction. And then they average these masks to get the final silence. The advantage is that they do not need to have access to the model internal outputs, intermediate outputs, but the downside is that it takes a lot of time to compute. If you have 10 detections in your image, you need to do 50,000 forward passes to explain the whole image. And when it comes to the localization and faithful metrics, we get more or less mixed results. But what we really gain here is the time variable that is way more efficient. Here's just some more results where we can observe what happens when you place the bottleneck in different layers of a YOLO network. We see that as we get closer to the input, the explanation gets more pixelated and more localized because we do not need to upscale it that much. But if you are in the bottom of the network, we have more semantic features. So it's a trade-off between the two things. Usually people go for the last layer that has more semantic information. No image, apparently. It's supposed to be one, but okay. We also do some kind of ablation to evaluate how each term of the loss function affects the explanation. Here, when you try to explain only the localization, we get this kind of silence. When you try to explain only the semantics, you get this. And when you use both terms, you can see that you have the complete explanation for the model prediction. I'm wondering what image was here. Enough important. Okay, so one of the problems is that it was only applied for classification. We also use it for detection. And the other problem is that you need access to the model intermediate activations, and thus it's not agnostic to the method, to the model. So the idea here is try to propose a new method that brings the bottleneck directly to the input image. Because if I can bring it to the input, I can apply it to any method that I want, to any model that I want, either CNNs or vision transformers, anything, we more or less solve it. So by doing this, we propose this new work that is called Information Bottleneck with Input Sampling for Attribution, where we pick both the ideas from the rise, and from the IBA. Here, what we have is multiple input masks that will use as perturbation in the input. But the difference is that we optimize each of these masks using the Information Bottleneck Principle. As I said before, computing the mutual information is not an easy task, and it relies on assumptions like Gaussian assumptions that we cannot make directly in the input. So what we do here is to fault some kind of heuristics to achieve the same objective. Each of these masks are generated in a differentiable way, and we optimize them using the cross entropy between the prediction of the masked image and the original prediction. But we try to squeeze the information that the mask contains by penalizing its absolute value. So we are trying to make the masks as sparse as possible while you maintain the cross entropy loss, while you also penalize the cross entropy loss. And you also add another term here, that is the total variation of the mask, to avoid them to be localized in the spurious notations, in spurious locations. So that's basically it. You generate a bunch of images, you optimize each of them, and by the end, you just average the optimized versions to get the final silence. In the rise, you need 5,000 so non-optimized masks. Here, we just use 20, and you only do 10 optimization steps. So again, we gain a lot of time by doing this. You also have the the advantage to be model agnostic. You can operate directly in the input. So this is the kind of explanations that we have. These are for classification models again. We have an image that has a spider and a bird, and you see that by changing the target in the cross entropy loss, you can identify why the model classifies it as a spider or as an indigo bird. Since we are trying to achieve the information bottleneck without explicitly computing the mutual information, we still need to analyze if what we are doing makes sense. So it's just to visualize what happens when you are optimizing the masks. Here is when you keep a beta of 1 divided by k. K is just a normalization factor. And as you train, as you optimize the bottleneck, you see that the information is getting more and more squeezed, I would say. And if you increase the beta, you see that the same 10 steps reduces more information. But the thing that is important is to observe these curves here. We tested it only for VGG and ResNet. But you see that this is the mutual information that we computed between the original image and the image after you apply the masks. And you see that as the optimization steps goes on, the mutual information between these two things actually decreases. And it decreases faster as you increase the value of beta. So what we are doing touches the objective of the information bottleneck principle, even if you are doing it indirectly. So it still makes sense to do this. Another thing that is important is that as you optimize the masks, the value of the original logit needs to remains the same. And it's something that we also observe here. Even though you are optimizing the masks, the probability of the original class is kept more or less constant. So empirically, you can evaluate that we are in fact achieving the information bottleneck objective. The metrics to evaluate Ibiza, that is for classification models, are very similar from before. These are deletion and insertion with order name. The literature is not well established on this. They use different names for the same thing. But basically, we start to remove the most important pixels in the case of the morph. For instance, the pixels here highlighted in red, it will be started to be removed, and you observe how the logit for the original prediction behaves as you remove. If this pixel is super important, we expect this logit to drop really fast. Thus, morph as close to 0 is better. On the LERF, we start to remove the least important pixels. So we start to remove information for these regions that the silence map point as no important. And when you do this, you expect the value of the logit to not drop. And thus, a high value for the LERF is a good thing. Ideally, 1 is the best one, because we are representing the area under the story. So this is just an example where an image where the morph is 0.12 and the LERF is 0.72. This is the comparison with the other methods. Basically, just compare with RISE, IBA, and GradCan, because these are the two methods that we try to fuse and see if there is a improvement on that. RISE is also model agnostic, but it takes, again, some time to compute an attribution, and we can do it way faster. And as I discussed before, we still have the ability to control how strict or how sparse the bottleneck is by tuning the beta parameter. As you increase the value of beta, you see that your explanation gets more and more sparse. Another thing is regarding the number of masks that you need to use, and also the number of optimization steps, because one might wonder if, okay, you are using only 20 masks and 10 optimization steps, but if you start using way more masks, maybe you get better results. And we see that this is not actually what happens. As you increase the number of masks or the number of optimization steps, you see that the performance in terms of the morph and LERF metrics does not improve. So if you use some kind of elbow method to determine the optimal parameters, you see that only 20 masks and 10 optimization steps are more than enough to generate the explanations for classification. And another thing is that even though we are using CNNs because we want to compare with the previous methods, this could also be applied to vision transformers because we are only operating in the input. Okay, so now we are going more towards the end, which is more or less the final work that I have done. So just to reevaluate the taxonomy of the attribution methods that we have been discussing, first we started with the IBA. In IBA, you need both access to activation maps and to the final output of the network to compute the salience. So it's not encoder agnostic and is also not decoder agnostic. You need both things to compute an attribution. When you move to RISE or Ibiza, everything is operated on the input, so you are encoder agnostic, but you still need to observe the final output of the network to generate the final salience map. So we are calling it encoder agnostic, but not decoder agnostic. But what if we can generate an explanation that neither depends on the intermediate activations nor the final output of the network? And then we would have a method that is both encoder and decoder agnostic. I couldn't explain only the encoder. And it's basically what we decided to do. Maybe you wonder what would be the advantage of doing this, but it's actually the only method that solves my problem, more or less. And this is when we propose the pairwise Ibiza. Before we are going to use more or less the same loss. We are penalizing, we have multiple masks in the input. We are trying to optimize these masks by both penalizing the absolute values of it and also the total variation. But before we had the cross entropy between the original prediction and the prediction of the masked inputs. But here, what we are going to do is to remove the cross entropy and use some kind of alignment loss. In this case here, I first illustrate for visual language models, for instance, CLIP, because it has a very cool application. If this is the embedding, HM is the embedding of the visual encoder of CLIP, and HT is the embedding of a text that you pass to the text encoder of CLIP, you can use this loss to align these two embeddings. And then your mask will be optimized to explain in the image what is described by the text. All right. We basically do the same thing, multiple masks, each of them optimized by a number of steps, and you average them out. So if you pass, for instance, the phrase, the image of a bird, to this encoder and generate embedding, you can then find the masks that explains this text. And it's basically what we do in this work here. Just to repeat it. But here we have a more modernized version of the image, where we have the text, you pass to the text encoder, you generate the embedding, then you try to find the mask that align these two embeddings. But the thing that is important here is that this vector, this embedding, it comes from the text encoder, but it is just a vector. It could be from anywhere you want, more or less. It could be, for instance, from the image itself. I pick the encoder, use the masked version of the image, and generate a representation. I can also pass the image itself to the same encoder and generate a target encoder here. It not come from the text, it comes from the image itself, and then I can explain why was this image encoded this way without having a final task, without having a downstream task. More than that, I can also pick one image, another image, and generate the embedding. And then my explanation will basically say, why are these two images similar? As you can see here, we have on both images a call, and the call is highlighted by the method. If you want to go a bit further, you can also change your alignment loss to not promote alignment, to instead promote disalignment between these two images. And then when you do this, your optimized masks, you explain why are these two images different. And thus, by removing the need for the downstream task outputs, we are now just able to explain in a more different ways. Okay, and since you also have this way of computing what is similar and what is different, we also have this kind of contrastive explanations when you subtract them both. You can see both what is similar and what is dissimilar between these two images. And how do we evaluate this? Not yet. We also have the loss function that we use for PBISA, because we have a catch here. Before, we needed to set the beta and fit parameters by ourselves. We defined how strict or how sparse the bottleneck is. But here in this work, we also are learning now these parameters, beta and phi. Use this kind of function here where you start these parameters as 0, and you penalize both then the explanation, and also you add them to the loss. So in your training, they try to balance themselves to find the optimal operation point. So now the parameters are learned during the process, but you can still set the parameters to a determinate value if you want. This loss that promotes alignment between the target embedding and the mask embedding is often the cosine similarity, and it works fine. We can try other losses, but I recommend the cosine similarity is the one that makes more sense. And when you want to find differences, you just use the cosine similarity to promote this alignment. It's not very different. So these are more results. This is a result for the visual language task. You have here the target text that is used text that is used to generate the silences for each of these images. And when you compare with the state of the art, we test it in 3 different data sets, and we see that we get the best results compared to the modern state of the art. These metrics here, confidence increase and confidence drop, they are also faithfulness metrics. Basically, it's very similar to before. We just remove what is considered irrelevant from the image and see if it matches the original prediction. We also have some examples here for image similarity. Since it is model agnostic, it's very easy to evaluate for different scenarios. So when you ask ResNet why these two images are similar, we have a salience map that is something like this, focus on spurious parts of the image. But when you ask for a facial recognition model, you see that it really focuses on the face. And this kind of capability is particularly useful also to evaluate image retrieval, because retrieval is basically done based on the similarity between the images. So you can also use it for retrieval. Here we compare on 3 data sets again against other state-of-the-art method. This one is also model agnostic, but we see that we get way better results in all data sets and all models that we tested, not only for CNNs, but also for VITs. See anything? And finally, we have the encoder-only explanations. As I said before, you can use the target embedding as the embedding of the image itself. And with this, we can explain both supervised models, but we can also explain self-supervised models. These are not trained with a downstream task in mind. They are just learning representations. And you can visualize if these representations, they align with human understanding or not. And for this, we not only did this qualitative analysis, we also compute some kind of metrics. First, we try some localization metrics to see if the explanation generated matches some human annotation, which is the reason why we use ImageNet S, is a subset of ImageNet that has segmentation masks. And you see that Dino V1 usually matches the human understanding better. Another thing that is interesting is that PBISA, even though we are not using the final output of the network, can also be used to explain the classification of these methods. And just to finalize, now for really finalize, my work was supposed is on pathology. But pathology, they rely a lot on the use of the foundation models, and explaining how you extract features for the patches is not trivial. It's not something that people do. And thus, in this work, we evaluated using PBISA. We evaluated if the explanations generated for these foundation models for pathology, they match human annotation. Just to clarify, the foundation models that we tested here, they are all vision language. So we pick a data set that has semantic annotation, we create a prompt, use this prompt to generate the silence map with PBISA, and then we compare it with pathologist annotation and see if the things match. And basically what we see is that when evaluating faithfulness to see whether the model relies on the human annotation or the silences more, we see that it relies more on the silences, of course. Another thing that we saw is that there is no overlap, no spatial overlap between the two things. So these models are trained in a way that they are learning discriminative features that does not necessarily match human understanding, which may be a problem or not. Maybe it's just new cues that you can somehow leverage for our understanding. And that's basically it.